deadlock prevention and deadlock avoidance algorithms are overly cautious in the sense that they refrain from taking many actions because they're afraid that a deadlock might occur. In reality, deadlocks rarely occur. So another approach is to let the deadlocks occur, since they're very infrequent, and then if it occurs, take care of it. So these are typically the deadlock detection algorithms. So we need a recovery scheme in such algorithms. How to first of all detect the existence of a deadlock? So if you have single instance of each resource type, we can work with what we call a wait for graph. So wait for graph is similar to the resource allocation graphs we discussed earlier, but this time we don't have the resource types in the graph. The graph is composed solely of processes. An example is given here. The graph on the left is the resource allocation graph we had been working with. So we have the processes in circles that are making requests to resource types, which have single instances, by the way, in squares. In the case of a wait for graph, actually what we're doing is we're dropping these square resource type boxes and combining the incoming and outgoing links to show the relationship between the processes. For example, here P2 is waiting for P3 in the wait for graph because in fact P2 is waiting for R4, which is assigned to P3. So similarly, P2 is also waiting for P5, as you can see here. Or P1 is waiting for P2. Or P4 is waiting for P1. Or P4 is assigned R5, which is being waited for both by P2 and P3. Therefore, both P2 and P3 wait for P4. So, in the wait for graphs, we have only the processes and there are the wait links between the processes. Like if Pi is waiting for Pj, then we have this arrow. Now, with the wait for graph, we can easily detect a deadlock by checking the cycles. If there is a cycle, then there's definitely a deadlock. However, how do we run these algorithms and how often we run these algorithms? Because typically the cycle detection algorithms in a graph with n vertices has a complexity of the order n square. So we don't want to run an O(n) square algorithm very frequently. So how do you work if you have several instances of a resource graph? In that case, we have an algorithm quite similar to the banker's algorithm. So I will go over this one very fast. We can have the available vector, which is a vector of length m for all resource types. We have the allocation matrix as we did before, and also the request matrix. So these are very similar to what we already did in the banker's algorithm. The detection algorithm is also similar. So again, we have the work and finish vectors. Work is initialized to available. This time, finish is set to false if the corresponding process has some resources allocated to it. But if a process has no resources allocated to it, then definitely it's not in a deadlock, because a process that does not hold any resources cannot be causing a deadlock. Therefore, for such processes, the finish value is true. For all others, finish is initially false. Then, in this finish vector, we search for a process Pi, which is not finished yet, and what it requests to finish is less than or equal to work which was initialized to available. In other words, we're searching for a process which has not been finished yet, but can be finished with the resources in hand. And you repeat doing this for all processes. If there are no such processes, then you skip step 3 and directly go to step 4 because everything is finished, so we should be looking at the result. But let's have a look at stage 3. So if there's such a process, again similar to the banker's algorithm, you add the set of resources allocated to that process to the work vector, which was containing the list of available resources, and set that process to true because that process can be completed. And this way you keep on repeating between stages 2 and 3 to see which processes can complete with the available resources. Finally, when you don't have any such processes left, you go to stage 4, where you check the finish array to see if there's any process with the finish value still as false. If so, those are the processes, there could be multiple of them, those are the processes that are in a deadlock. So we don't only detect a deadlock, but we also detect which processes are in the deadlock. This algorithm requires m by n square operations to detect whether the system is in a deadlocked state or not. Therefore, we don't want to run this algorithm very often. So let's look at this example. Let me also get the pen. So we are assuming that we have 5 processes, P0 through P4, and 3 resource types, A, B, C, with the given instance values. At any point in time, again, during the execution of this system of 5 processes, we have this given snapshot, and currently we don't have any available resources, A, B, and C in the available vector. They're all zeros. Is this system in a deadlock state or not? Now remember, the idea is to find if the processes can complete. But first remember, if a process has allocation vector all zeros, that's already set to true, but we don't have that case. So let's look at the others. We have no resources available. Is there a process that can still complete? As you can see, P0 can still complete because it doesn't request any resources to complete. Therefore, we can say we can get rid of P0, we can complete that. And the available matrix will be now 0, 1, 0, because we're putting all the allocated resources to P0, adding them on top of available. So, P0 is the first one to complete. Now, with the available resources as 0, 1, 0, is there any process that could complete? As you can see, P2 also does not require any resources to complete. So P2 could also complete. Okay, so its resources are also added to the available matrix, so it becomes 3, 1, 3. So P2 is also in the list. Note that I could have started as P2, P0. That's also fine, so that would be an alternative. But again, let me stick with this. So with the available resources as 3, 1, 3, is there any process that could complete? And actually, as you can see, all of them could complete because the number of available requests are 202, 100, 002, and all of these 3 are less than 313. So in the example here, we complete them in the order 314. You could come up with other orderings like 134, 431, 413. Doesn't matter. All of these are acceptable. The important thing is there is a way out of this state. So we're not in a deadlock. Okay? So this system is not deadlocked. Uh, Now, assume that P2 makes a request for an additional instance of type C. So this time we're changing the request request matrix where P2 is not 000 anymore, but P2 is now, let me just erase all these. So in the modified version, P2 is 001 here, okay? So is this system in deadlock or not? Let's see. Again, P0 can complete, okay? So the available becomes 010. Now, is there another process that can complete with available vector as 010? Not P1 because it requires 202, not P2 because it requires 001, not 010, not P3 and not P4. Therefore, if the request matrix of P2 is modified as 001, the system would be in a deadlock. P0 could complete, but the remaining four processes, P1, P2, P3, and P4, are in deadlock in this case. This is also explained here. So the question is, when do we run the detection algorithm, and how often do we run the detection algorithm? How often we run the algorithm actually is related to how often a deadlock is likely to occur. Of course, we don't know when a deadlock will occur. It's not a regular occurrence. But if you have a slight idea about how often it occurs, you may delay deadlock detection algorithm running that much. One other thing is, okay, we have run the algorithm, we have detected some deadlocks. How many processes are we going to roll back? And also, actually, which processes are we going to roll back? If you detect cycles in the graphs, what you can do is you can roll back one process per disjoint cycle, or better, if the cycles have a shared link. Remember the, for example, the wait for graphs. If the cycles have a shared link, just roll back one of the processes on that shared link, and you will be able to break two cycles by just rolling back a single process. So you should be careful with which process you're rolling back. That's also important. If the detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph. So we should not be, we would like to be able to tell which of the deadlocked processes, because there will be many of them since you have delayed the running of the algorithm for so long. There will be many of them. So which one actually created the cycle? Which one completed the cycle actually? One thing we can do is the following. The cycle is completed with the addition of the last link. And this occurs only when a process makes a request for a resource and it is blocked. It has to wait. So we can, for example, run the algorithm every time a process is forced to wait for a resource. But even this is a very frequent run of the detection algorithm. When you detect an algorithm, you can try to abort all the deadlocked processes, but this will be very costly. A better solution would be you abort only one process, and as I said, try to pick the one that's in the cycle of more than one cycles if possible, until all of the cycles are eliminated. Which process is to be aborted, that might also be decided according to these 6 concepts. One is you can look at the priority of the processes, and of course you don't want to roll back a process that is of high priority, so try to roll back a process that's of low priority. Another one could be when you roll back a process, actually you're rolling back, you're actually trashing all the actions, all the CPU time that was consumed by the process. Because the process had been running for some time. When you roll it back to the beginning, all the executions, CPU executions you have allowed for that process, they will be just discarded. You have to start all over again. So that CPU time is wasted. So you might be looking into that and, for example, try to roll back a process that has just started. Or if you know how much time is left for the process to complete, by the way, this is difficult to know, but if you know it, then you might, for example, pick the one which is the longest time to completion, because anyways it's not likely that it will soon complete. So give, that means higher priority to the processes that are about to complete. So just terminate another one so that this can have the chance to complete. You can look at the number of resources that the process has used. If a process has used a lot of resources, rolling it back means again wasting the time spent by those resources to fulfill the requests of that process. You have to anyways do it once again. So you might want to keep such a process rather than rolling it back. You can look at the resources the process needs to complete. So remember the need array? You can look at the need array, and if you see a process just needs a few resources to complete, you can keep that process and try to roll back a process which needs a lot of resources, because that process, even if you keep it, is likely to cause further deadlocks also in the future. So the processes that can complete with fewer number of resources might be preferred. You might look at how many processes need to be terminated to break the loops. Like either I pick this and this process, or this process will break 2 loops at once, that idea. Or you can look at the interactivity of the processes, because if you roll back a process that was interacting with the user, of course the user will be frustrated. So it's in many cases better to roll back a batch process, because the user is not directly interacting with those batch processes. With the resource preemption, you can, rather than terminating the processes, one other thing is you can preempt the process that was using a resource from that resource. So in other words, take the resource back. But which resource is to be taken from which process? That's a problem. We can try to minimize the cost, as we discussed in the previous slide. You need to roll back. Now, if you have taken snapshots along the way for the processes, so if you remember the safe state of a process, you can roll back to that safe state rather than rolling back all the way to the beginning. But the point is, did you take such snapshots? In the database systems course, you will, for example, learn such cases because you're trying to do some transactions. At some point, you might experience a problem, could be a deadlock or some other problem, and you want to cancel the operation. So if you have stored the value before the transaction, you can roll back to that. But such rollback operations there, both in database systems and also in operating systems, actually incur, for example, a cascade of rollbacks. That means you roll back this process to this point, but it was dependent on another process being at another point because they were synchronized. So if you roll this back, you should also roll that one back. But if you roll that one back to this point, you should roll this one back further and further and further. So this is actually a difficult problem to solve. And also, if you have such criteria, many of the criteria here define some fixed priority of the processes one over the other. So such things like directly priority based or the number of resources being used, whatever, or being interactive or batch. When you have such fixed criteria that make up the decision, it is possible that a process goes into deadlock, but a process cannot go into a deadlock by itself. Of course, it's in a deadlock with one or more other processes. But because of these fixed criteria, you pick that one as a victim. You roll it back. You temporarily break the deadlock, but the deadlock occurs once again. So again, when you run these same criteria, probably these criteria will pick the same victim again. So again, you roll that one back. So that process happens to be very unlucky, and it's always that process that is being rolled back. So this is, of course, something that not nice, which will end up with starvation of that specific process. So this will be the end of this chapter. Again, please have a look at these sections in your textbook.